Hey, this is Kaveen, Bubudu, and Yasindu presenting Smart Kettle using the ISR of a microcontroller. So, the presentation outline today is we're going to go over the proposed Smart Kettle, what it is, what are the features we have implemented, things along those lines. Then we jump into the technical aspect of the project. Next, we're gonna give you a little demo of the project. Then we come back to questions. Okay, so the proposed Smart Kettle is all things interrupts. So this whole semester we've been learning different aspects of interrupts. So we thought it would be a interesting thing to explore further in our project. So we have incorporated interrupts in two different ways. One, hardware interrupts for the shutoff mechanism. So basically you're looking for a rising edge in a particular temperature level, then the whole system shuts off. And the next one is software interrupts, which is implemented in the buzzer implementation, where when the water gets to about 95 degrees, the buzzer goes off for about 4 seconds to measure that timer. Measure that time. We have a timer in place, and that timer is going to utilize software interrupts in our system. Okay, so we're going to talk about this in more details as we go. So let's keep going. So what does it do, right? So we can sort of see excuse me. We can sort of see 4 different aspects of this project, right? Like key features of this project. First one is automatic shut off, where when the water gets to about 95 degrees, it shuts off automatically using hardware interrupt routine. Then we have a real-time temperature display where the consumer can see the real-time temperature using the OLED display and also the website that we created. Then we have keep warm function, where the consumer can opt in for that function, and if that function is turned on, the heater is gonna restart when the water temperature level goes below 88 Celsius. So your water never gets too cold because of it, because the process is going to restart if the water isn't hot enough. And we also have some user alerts. So we have a buzzer going on for 4 seconds when it reaches 95 degrees, when the water reaches 95 degrees, right? And then we have some LEDs that indicates different temperature ranges, as well as system notifications such as system errors. Okay, moving on to technical description. So these are the hardware that we used. We used the Arduino Uno Wi-Fi revision 2 version, which has an upgraded microcontroller in it compared to the base version. Then we have an immersion water heater that has a wattage of 300, and we also utilize a relay module that can decouple the DC circuit from the AC circuit, so that we can drive the heater using that relay. Then we have a temperature sensor. We also have a display module where the users can see the readings in real time. And also we have an active buzzer that goes off for about 4 seconds when the water is ready. And finally we have some good old electronics to make this work, such as LEDs and 1K resistors. Okay. We also needed some software, and all of these were available in the Arduino store or library manager. Moving on, so let's talk about the power of this project. So before we mount the circuit, we did a little bit of simulation to make sure that we're not going to smoke up any of the circuit parts. So in your left side is the Arduino DC circuit, where like this 6.25 volts is like the input for the Arduino, and then it has an internal resistance of 25 ohms, which we discovered from just by googling, and what it does is it creates a current that goes through this coil in the middle, which is the relay, right? So we all know that when the current flows through a coil, that creates a magnetic field, and that magnetic field is just strong enough to pull flip that switch in the right side, and once that switch is flipped, that circuit can have a flowing current. So that way we can control that AC circuit. So notice that the right side circuit is powered by 120 ohms with 60 hertz voltage source. Then we also have some probes of the oscilloscopes to just to see what's going on. So notice there is a 23.8 ohms resistor, which is the load resistor, which means that it represents the heater that we're using. So we did some calculation, and it ended up to be about 23.8 resistance in the water heater. So the green the green voltage meter can monitor how much voltage is going on there, and then the green is the emitter that's keeping track of the current. So right now the switch is closed so that you have a current flowing, so that you can see that the output, which is the orange, is like you have a sinusoid going on there, but if you wait a little bit, when the switch is closed right now, the orange line is a flat line, which means there is no current flowing through. And then also, if you did some math, the power of the water heater should be about 300 watts, and then you can sort of see that by applying, power equals voltage times current. So your current is between 2 to 4, then you have your peak voltage to be about 84 volts. So that tantamounts to about 300 watts for the resistor. Okay, so let's move on to the next slide. So this is the data flow diagram. So we have the Arduino in the middle, and you can see that there's a control signal to the relay, and that is where the ISR can shut off things. Basically, the relay control signal is it's located at the ISR so that it can turn off that signal to interrupt and to shut off the system. Then we have the OLED screen, which is utilizing I2C communication. So you have a data line and a clock signal going from Arduino to the OLED screen. Then we have a temperature sensor that has a sensor data line connected to the Arduino, and that data is streamed into Google Firebase real-time database, and then that database information data from that database is pulled into the web portal we created, and then the consumer can log into that web portal and then turn on the keep warm signal if they want to. If they do, the water is gonna heat up over and over again, and also Arduino is controlling the LED panel as well. Moving on to the next slide. So we have some limitations. So the way we created a rising edge for the hardware interrupt was a little bit artificial, because like if you wanted to create an intrinsic analog signal like that, you would have to get through some analog circuitry. So we have that designed. So if anyone's curious, we can explain it more, but I'm not gonna explain it here. But feel free to ask more questions if you're curious, like why we have a suboptimal solution rather than the optimal solution to create a rising edge for the interrupt service routine. Now is the demo time. So after the demo, you can ask us questions, and we would be happy to answer your questions.